Alright, hello and welcome to Unit 5. And in Unit 5 we swap gears a little bit and we talk about probability, which is something that you are probably at least a little bit familiar with. Okay, so here's our first scenario I want you to think about. Let's suppose that you're on a desert island and you are playing dice with another castaway. I don't know why, of all the things you could have brought with you on a deserted island, you chose to bring dice, but you have dice. Okay? The winner's prize will be the last banana on the island. And here are the rules of the game. Each player will roll a die. If the largest value shown is a 1, 2, 3, or 4, then player 1 wins. If the largest value shown on those two dice is a 5 or a 6, then player 2 wins. And so I want you to think about what your guess would be. Who do you think is more likely to win? Player 1, player 2, or do neither one of them have an advantage? Are they equally likely to win? Okay, so most people guess player 1. It kind of makes sense because player 1 wins if a 1, 2, 3, or 4 is the biggest number shown. Seems like they have more options, right? Well, let's say that we played this game 20 times, and here are our results. And I actually have played this game with some students before, and these are pretty similar to what you would see. Here's what we actually find. In our game, player 1 actually only won 40% of the time, and player 2 actually won 60% of the time. Okay? So these numbers right here are what we call experimental probabilities, right? So experimental probabilities are when we find probability by actually conducting an experiment. So there's no guarantee of what's going to happen. We actually take some steps to find out, right? And so when we write our probability, there's a number of different ways that we could write it. We could write it as a percentage, as was shown here. We could write it as a decimal. So 0.40 is the same thing as 40%. We could have also written this as a fraction. Player 1 won 8 times out of 20. All of those would mean the same thing. Okay? So, what was done next in question 3 is the game was played many, many times. So this time, the game was played 320 times. And I want you to think about why that might be a good idea. So if we saw results with only playing the game 20 times, that's not very many times. What if our results were a fluke? So when we look at playing the games many, many times, we're more likely to see what's really happening. And so when we played the game 320 times, what we found is that player 1 won 43% of the time, and player 2 won 57% of the time. I would have more faith in these numbers because they came from a larger data set, right? And that's what we refer to as the law of large numbers, okay? And so what you'll notice is that those numbers got closer together, but they're still not the same. Player 1 and player 2 do not have an equal chance of winning. That's what our experimental probabilities are showing. Okay? It actually looks like player 2 is more likely to win. So in question number 4, they say, let's determine the true probability of player number 1 winning. And the way we do that is we list out all the possible rolls that we could get when we roll 2 dice. And so this square right over here is what we call our sample space. And our sample space is just a list of all possible outcomes that we could have from an experiment. So for example, we could roll 2 dice and both of them could be a 1. We could roll 2 dice and the first one could be a 4 and the second one could be a 5. So these are all the possible outcomes. Okay, so when we list these out, what we're looking at is how many total outcomes are possible. Well, if you count all those different squares up, there are 36 possible outcomes when you roll 2 dice. So that's why there's a 36 on the bottom of this fraction here. Well, what's the probability of player 1 winning? Well, the probability of player 1 winning comes from if a 1, 2, 3, or 4 was the highest number rolled. So if we circle those options, that would be this option, this option, this option, and this option. That's 4. Be here, 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 and what you'll notice is that out of 36 total options, only 16 of them result in a win for player 1. So my probability of player 1 winning is 16 out of 36, which written as a decimal is 0.44 or 44%. So player 1 has a 44% chance of winning. This is what's called our theoretical probability, because in this example, we didn't actually perform the experiment, right? All that we did was we made a list of what was possible to happen. Okay? Well, let's compare that to our experimental probability. They weren't exactly the same, but they were pretty close. So here's what I want you to remember. When you perform an experiment, the more you perform it, the closer you will get to that theoretical probability. Okay? Alrighty here. So what are some different ways that we can record probabilities? Well, the most common way that you will see probability recorded is in a probability model, which is shown in this table right here. So what is a probability model? It's a list of all the different outcomes and the probability that each outcome occurs. So when we read this example here, it says the Pew Research Center reported that among mothers, family size is shrinking. Suppose we are to randomly select one mother between the ages of 40 to 44, and we record the number of children she has. Okay? So the possible outcomes here are she could have 1 child, 2, 3, and 4 plus. Okay? The numbers at the bottom are the probability that a mother fell into each category. So 22% of mothers that were polled had only 1 child. Okay? That's how we would read this table. What makes it a probability model is 2 things. These probabilities that are shown have to add up to 100%. Okay? So if I had added a different category at the end, like let's say I had added 5 children, and I said that was 0.24, this model would no longer make sense, right? Because those probabilities don't sum to 100. Alright, so the other thing that has to happen is that you have to make sure that there are no negative probabilities, right? So the smallest probability that you could ever have is 0, and 0 just represents that something is impossible. It can't happen. It doesn't make sense to have a negative probability. Okay? So part B, explain why events have 1 child and have 2 children are mutually exclusive. Well, what does mutually exclusive mean? Mutually exclusive means that 2 things cannot be true at the same time. Okay? So you can't have exactly 1 child and exactly 2 children at the same time. It's either one or the other. That's why they are mutually exclusive. They can't occur together. Okay? Part C says this. Find the probability that a randomly selected mother has less than 2 children. Well, on this model, less than 2 falls right here. So the probability of having 1 child is 0.22, or you could have written that as 22%. That's just a personal preference, completely up to you. I do want you to notice the notation here. Whenever you see a capital P, that stands for probability. You will see that in your homework. They won't always spell out the word probability. Part D says this. Find the probability that a randomly selected mother has 1 or 2 children. The key word there is or. When you see the word or, it means add. So the probability of 1 child is 0.22. The probability of 2 children is 0.41. To get the probability of one or the other, we're going to add those numbers together to get 0.63 or 63%. Okay? Part E says this. Find the probability that a randomly selected mother does not have 4 or more children. So a lot of people will miss questions like this because they don't pay attention to the word not. When you see the word not in a probability, that is what we call a complement. And here's what we mean by that. If I say, what's the probability that someone does not have 4 or more children, that means what's the probability that they fall in any of those 3 categories? Well, in a problem where you had bunches of categories, it could take you a long time to add all of that together. So what we can do instead, when we have a complement, is we can say, well, it's everybody but this category that I just X'd out. So what I can do there is I can say I'm going to take 100% of people and subtract out the 13% that fell in that category. Well, what percent does that leave me for everybody else? 87%. And so the notation for a probability involving not will have a little C with it, and that C stands for complement. It means take out this group and see what you're left with. Okay? So on our next page, let's talk about what the probability of being a brown-eyed female would be. Okay? So in question number 1, we have some class. We're not told anything about that class, but there are males and females who have blue, brown, or green eyes. And below what we have is something called a two-way table. And a two-way table shows two different variables. So on we could call it the y-axis, going up and down, we have gender, male and female. Going left to right, we have eye color, blue, brown, and green. Okay? So the way that I would read this table is I would say, in this class, there was one male with blue eyes. There were 3 females with brown eyes. The numbers outside the table are actually your totals. So in total, there were 5 males in this class, there were 5 females, and there were a total of 10 people. You'll notice that the bottom also adds up to 10. There were 3 people with blue eyes, 6 with brown, 1 with green, for a total of 10 people. Okay, so question number 2 asks us to find several different probabilities. So the first one just says, what's the probability of picking a male out of this class? Well, there are 10 total people in this class. 5 of those 10 are male, so 5 out of 10 would be my probability, or I could write that as 0.5 or as 50%. Okay? These are your simple probabilities, and to get simple probabilities, you just count the total number of people that goes on the bottom of your fraction, and then on top is the number of people in that category. Question number 3 gets just a little more complicated. It's asked us to find the probability that someone is a male or a female. Well, what does the word or mean? The word or means add. Okay? Now, here's what I want you to think about. The reason that we are just able to add these together, and it's that simple, is because male or female are considered mutually exclusive. Okay? There is no one in this table who is listed as being male and female at the same time. So all we have to do is add together the 5 out of 10 males plus the 5 out of 10 females to get a total probability of 10 out of 10. What does that mean? We have a 100% chance in this class of picking a male or a female. Well, what about the probability of picking someone with blue or brown eyes? Again, those two things are mutually exclusive. You can't have blue or brown eyes at the same time. So to get that probability, all we have to do is add together the people who have blue eyes, well, there's 3 of those, plus the people who have brown eyes, there's 6 of those. Well, 3 out of 10 plus 6 out of 10 gives us 9 out of 10. So we have a 90% chance of picking someone with blue or brown eyes in this class. It does get a little more challenging if we have a situation that is not mutually exclusive. So for example, if I asked you to find the probability that someone is male or they have blue eyes, I'm going to circle this on the table. So here's the people who are male. Here's the people who have blue eyes. Here's the problem. If I just add together the 5 total males and the 3 total people who have blue eyes, this person right here fell in both categories. So I'm going to be telling you 5 plus 3 is 8 when there's actually not 8 people being counted here. There's actually only 7. So here is our formula when something is not mutually exclusive. It's the probability of A plus the probability of B minus the probability of A and B. So let me explain that in this context. A in this case stands for gender. So we are looking for the probability that someone is male. Then B stands for their eye color. So in this case, we're looking for the probability that someone has blue eyes. But because we had someone who fell in both categories, we have to subtract out the overlap. So we are still doing 5 over 10 plus 3 over 10. But we're going to subtract out the one person who got counted in both categories so that we don't accidentally say there were 8 people counted when there were only 7. Okay, so our total probability here is 7 out of 10. Well, let's talk about female or brown eyes. So if I circle this on the table, what's the probability of a female? There are 5 females, and there are 6 people with brown eyes. Well, if all I do is add that together, 5 out of 10 plus 6 out of 10, that would be 11 out of 10. That's a probability that's over 100%. So that can't be right. What's the problem? Well, there are 3 people right here who got counted in both categories, right? So we need to subtract out that overlap, which leaves me with 8 out of 10, which makes sense. There were only 8 people who were actually counted. Okay? Question number 5 says this. Find the probability that someone does not have green eyes. So they actually wrote that out in words. Here's another way that I could have written this. I could have said the probability of green complement. That little C means not. Well, what's the probability that someone does not have green eyes? That means I'm taking out these people right here. That leaves me with 9 out of 10. Okay? What's the probability that someone is not male? That means the probability of male complement. So that means I'm just taking out the males. Well, there's 10 people. 10 minus 5 leaves me with 5 out of 10. Okay? All right, so what I have here for you in these top 2 boxes is just your rules written out in case you need to see those. Okay? And then we are going to skip the next page. We're going to talk about some traffic. So a local news station recently added a traffic jam calculator and a snow day calculator to their website. So what they've done is they've given us a probability model. How do I know it's a probability model? Well, if I add together let me back up there for a second. I just proved myself wrong. This is not a probability model because it does not add up to 100%. So if you add together 0.4 plus 0.2 plus 0.3 plus 0.5 plus 0.7, that is way over 1. So this is not a probability model. However, it does give us an idea of what's happening on each day of the week. So when I read number 1, they asked me to find the probability of a Thursday traffic jam, and it's 0.5 or 50%. How would I interpret that? The way I would interpret that is there is a 50% chance of a traffic jam on Thursday. Or another way you could say this is if I picked 100 random Thursdays, I would expect to hit a traffic jam on 50 of them. Is it a guarantee that I will, see that happen exactly 50% of the time? No, but I would expect that to happen. Okay? What's the probability of a Friday traffic jam? 0.7 or 70%. So how would I interpret that? If I were to pick 100 random Fridays, I would expect to hit a traffic jam on 70 of them. Okay? So here's the question. Are the events Thursday traffic jam and Friday traffic jam independent? Well, what does the word independent mean? If you think about the way we use it in normal language, if I say I am an independent person, it means I don't rely on other people. And it means something similar in probability. What it means is that Friday's events don't depend on what happens on Thursday. They don't rely on Thursday. So knowing whether or not there was a traffic jam on Thursday doesn't change the probability of a traffic jam on Friday. Okay? And so if I then ask you to find the probability that there is a Thursday traffic jam and a Friday traffic jam, all that I have to do, because those two events are independent, is multiply their probabilities together. So when I see the word or, I'm going to add. When I see the word and, I'm going to multiply. So 0.5 times 0.7 gives me 0.35. Okay? You can do this for more than 2 days. If I want to take the probability of a traffic jam every day of the week, I'm going to multiply all 5 of those probabilities together, and I get the decimal point 0084, which, if I wanted to write that as a percent, would be 0.84%. So notice there, when I go to a percent, I just move the decimal over 2 times. Okay? So it's not very likely for me to hit a traffic jam every single day of the week. All right, well, think about this. What would be the probability of no traffic jams all week? We're not given that information explicitly, but if we're told that there's a 40% chance of a traffic jam on Monday, that would mean that there is a 60% chance that there isn't one. If we're told there's a 20% chance that there is a traffic jam on Tuesday, there's an 80% chance that there isn't one. So we're just multiplying together all of those complements to get a probability of 0.0504. Okay? Well, think about question 8. How would I find the probability that there was at least one traffic jam this week? Well, when I say at least one, that means there could have been one traffic jam, there could have been 2, there could have been 3, 4, or 5. That sounds like it would take me forever to calculate. And it does, unless you think of a shortcut. The probability that there is at least one traffic jam just means that I am subtracting out the probability that there were none. Okay? So I'm taking 1, which represents 100%, and I'm subtracting out the probability that there were no traffic jams, which we already calculated. So when I do 1 minus 0.0504, that leaves me with a 94.96% chance that I'm going to hit at least one traffic jam this week. So I need to plan on hitting at least one. Okay? Let's talk about our snow day calculator for this week. So this one right here, again, is not a probability model. It does not add up to 100%. So what's the probability of a Thursday snow day? 0.7, right? That's pretty easy to read from the table. What's the probability of a Friday snow day? 0.6. And so here's the question. Are the events Thursday snow day and Friday snow day independent? And they are not. And I want you to think about why. Okay? I'm a teacher. If I know that we had a snow day on Thursday, then there's a very good chance that we have a snow day on Friday, right? Because that snow may not melt. It's obviously already very cold. All of those things increase my odds of having a snow day the next day. On the flip side, if I don't have a snow day on Thursday, then I'm less likely to have a snow day on Friday, right? So these are not independent. Because they are not independent, there is some extra piece of information that I need to know in order to calculate the probability of a Thursday snow day and a Friday snow day. I need to know how much more likely it is if I do have a snow day on Thursday that I get one on Friday. And they don't give me that information. So therefore, I can't just multiply these together. In fact, until they give me that information, I can't calculate those odds. Okay? All right, and again, at the top here, I've got your rules written out for you here. So just a reminder, if you see the word and, you multiply your probabilities together. But that only works if your events are independent. If they're not independent, they have to give you more information in order for you to calculate that probability. If they don't, you can't answer the question. Okay? We're going to skip on down to the next page. So the multiplication rule that we just talked about actually applies to more things than just probability. It also applies to counting different numbers of items or different numbers of ways that I can do things. So let's say you went to an ice cream shop. So this ice cream shop in Don Trails Town is called 21 Choices. Why? Because they offer 21 different flavors of ice cream. Sounds like they're trying to copycat Baskin-Robbins there a little bit. Don Trail likes all but 3 of the flavors that the 21 Choices offers. He doesn't like bubblegum, butter pecan, or pistachio. I can't blame him because I don't think those would be my first choices either. So a 21 choices basic sundae comes in 3 sizes, small, medium, or large, and it includes 1 flavor of ice cream and 1 of 12 toppings. Dontrell has enough money for a small or medium basic sundae. How many different sundaes could Dontrell order that includes only the flavors that he likes? So I'm going to reword this question. What I am trying to figure out is how many different ways he could build a sundae. And here's what I have to consider. I have to consider the size and the flavors and the toppings. So anytime you are saying the word and, that implies multiplication. Well, how many different sizes does he have the option of? 2, small or medium. How many flavor options does he have? Well, there are 21 total, right? But we're told at the very beginning that he doesn't like 3 of them, so that leaves us with 18 flavors that he's going to choose from, and then 12 toppings. So 2 times 18 times 12 means there are 432 different sundaes that Dontrell could build. All right, let's look at a different scenario. Let's say that Dontrell decides to order a cone with 3 scoops of ice cream instead of a sundae, and he prefers to have 3 different flavors for variety, and he considers the order of the flavors on his cone to be important. So maybe he doesn't want the chocolate to drip down on the strawberry, so he wants to put the chocolate on the bottom. So the order is important. Okay? Here's why I'm emphasizing that. If the order is important, this is what we call a permutation. So a permutation is an arrangement of items or events where the order matters. Okay? So how would I solve this problem? So I'm going to line up how many choices does he have for his first scoop. Well, he could choose any of the 18 flavors that he likes. How many choices does he have for his second scoop? We're told that he wants 3 different flavors. So let's say he chooses chocolate for the first scoop. He's not going to choose chocolate again. That means there's only 17 options for the second scoop. Let's say he chooses strawberry for his second scoop. Well, now strawberry's out too. He only has 16 options for his third scoop. So if I multiply those together, 18 times 17 times 16 gives me 4,896. Okay? Let's say that you don't want to list that all out. There is actually a permutation button in your calculator, and I'll show that to you. Okay? So when you go into your calculator, what you're going to do is you are going to click this math button right over here. Okay, so that's what I'm clicking. I go to math. I'm going to click the right arrow over to probability. And your calculator may say just PRB instead of PROB, and that's fine. They're the same thing. And I'm going to go down to where it says NPR. That P stands for permutation. N and R stand for 2 numbers that you're given in the problem. So N stands for the total number of options that you have. R stands for the number of them that you're actually choosing. So once I click that, I would click 18 first because there are 18 total items. And then I would put 3 in the second box because even though there are 18 options, I'm only choosing 3 of them. And you'll notice that also gives me 4,896. Now, if you have a slightly different calculator model, it will make you put this in a little bit differently. What you'll have to do is you'll have to type the 18 first, and then go click the math button, go over to probability, down to NPR, and then type in the 3. But it still gives you the same answer. Okay? Okay, so there is a third way that I could have written out this question to get the answer, and that is using something called a factorial. So factorial is represented by an exclamation point. So if I did 18 exclamation point, that would mean 18 times 17 times 16 times 15 times 14 all the way down to times 1. So it's every number multiplied together 1 through 18. Well, that's not what we did in this problem. We just did 18 times 17 times 16. So if I wanted to represent this with factorials, I could say take out 15 and below. So 18 factorial divided by 15 factorial is the same thing as 18 times 17 times 16. And I will also show you that on your calculator, because your calculator will handle factorials for you. So if I go into your calculator and I type the 18 first, I click the math button again, I go over to probability, you'll notice the fourth option down is an exclamation point. So if I click that, and then I do divided by 15, math, exclamation point, boom, I get the exact same answer. So there's 3 different ways that you can get the same answer when you're dealing with a permutation. Okay, so let's look at Wendy's here. So in 2009, Wendy's had a takeout bag, which said, we figured out that there are 256 ways to personalize a Wendy's hamburger. Luckily, someone was paying attention in math class. I'm actually old enough that I do remember this ad. But the question is this correct? Okay, so let's talk about it for a second. So is this a permutation problem? Well, what does that mean? Well, permutation is an arrangement of items. We are arranging some items. We're putting some toppings on a hamburger. But here's the key. If it's a permutation, the order of the toppings matter. So, for example, ketchup going on the burger before mustard, okay, would be different than mustard first, then ketchup, if it's a permutation. Well, does anyone actually care about whether you put the ketchup or the mustard on first? Not really, right? The order doesn't matter in this situation. The hamburger tastes the same no matter what topping I put on first. So this is not a permutation, okay? This is what I would call a combination. Well, what if I change it a little bit? What if I say Wendy's offers 9 topping options for their hamburgers? Choose your 3 favorite. List all toppings in a way they can be put in order. Well, if I tell you that they are being put in order, that's a permutation, right? So you've got to read those instructions carefully. So number 2, there's a few different ways I could get the answer. If I am picking my favorite 3 toppings and I am putting them in order on this hamburger, I could either do 3 times 2 times 1, because I'd have 3 options for the first topping. Once I put the ketchup on, I'd only have 2 toppings left for my second choice. Once I put the mustard on, lettuce is the only thing left, right? Well, 3 times 2 times 1 is 6. Well, if I didn't want to write all that out, I could also say, hey, that's 3 factorial, 3 exclamation point, because that's 3 times 2 times 1, right? The third way that I could get this answer on number 2 is I could say, well, if I'm putting it in order, that's a permutation, and I could go into my calculator, and I could find 3p3, and that would give me the same thing. And what that means is there are 3 total toppings. I am using all 3 of them. Okay? So on number 3, how many ways can you order a hamburger with 3 toppings if the order of the toppings does not matter? Okay? So they've given you a formula here. We're not going to go through that whole formula. But if the order of the toppings doesn't matter, it's not a permutation. That is what we call a combination. And so when we do this one in our calculator, we're going to hit almost exactly the same buttons, except for one slight difference. Okay? So there were 9 total toppings, so I'm going to click 9. I'm going to go to math, probability. This time, instead of NPR for permutation, I'm going to click NCR for combination. Okay? So if I had 9 total toppings, and I am choosing 3 of them, and I don't care about the order, there are 84 different options for how I could build a hamburger. Okay? So what you will find is that there are always less combinations than there are permutations. And of course it's going to log me back out. There we go. Okay. So, question number 4, what we are going to do is we're going to try to figure out the total different ways you could build a hamburger if you didn't care about the order of the toppings. Well, the first way is to get your hamburger plain with no toppings. That would be 9C0 because there are 9 options, but you're not using any of them. there's only one way to build your hamburger. That's a plain one, right? Well, what if you pick one topping? That is 9C1, and the answer to that is just 9. That makes sense because you could have a ketchup burger, a mustard burger, a lettuce burger, a tomato burger, and so on, right? There are 9 different toppings, so 9 different burgers. Well, what if you pick 2 options? Well, 9C2 would give you 36. That comes from the calculator. They do have the formula written out for you by hand, but I'll be honest with you, no one ever remembers it, so we typically just type it in our calculator. They did 9C3 and got 84. That's the one that we just did. So that's 9 options. You're putting 3 toppings on your hamburger, and so on, all the way up to the very end where somebody orders a burger with all 9 toppings on it. Well, if I add together all these different burger combinations, I get that there are actually 512 different ways that you could build your hamburger. So Wendy's actually sold themselves short. Okay? So here's what I want you to remember. Permutations are when the order matters. That's the NPR button on your calculator. Combination is when the order does not matter. That's the NCR button on your calculator. Okay? There will always be more permutations than there are combinations. Alright, so we're just going to walk through a couple examples here and then we're done. So Janine wants to set up a playlist with 8 songs on her iPod. Wow, that's an old example. She has 50 songs to choose from, including 15 songs by One Direction. Janine's iPod won't allow any song to appear more than once in a playlist. So how many different sets of 8 songs are possible for Janine's playlist? Assume that the order of the songs doesn't matter. So how do I know that this is a combination? Because it states the order doesn't matter. She doesn't care if a One Direction song comes on first or if it comes on last. So how many different ways could she build her playlist? Well, there are 50 total songs. She's choosing 8 of them. If you type that in your calculator, there are 536,878,650 different playlists she could build. Okay? Well, what about question number 2? What if she wants an 8-song playlist, but she wants to specify that she hates One Direction? She doesn't want any One Direction songs in the list. Okay? And she is going to let her iPod select an 8-song playlist at random. Well, what happens here? She has 50 songs, but she up front is taking out the 15 One Direction ones. So that only leaves her with a total of 35 songs. So now, when you type this in your calculator, you're doing 35C8, which is a much smaller number, 23,535,820. Okay? And then we are going to skip questions 3 and 4. And we are done for this unit. Please let me know if you have any questions.